All right, so this is the exam 1 review. So for the video, you get 1 page, front and back, handwritten. I don't care what's on there. You know, it could be words of encouragement, it could be example problems, it could be additional formula that you may think are easy, it could be integral or differential tables, just handwritten, no printed out stuff on there. So you're going to get the equation sheet that you've had from the beginning of class day 1, same way that it was included on the quiz. It's going to be right there as an attachment at the very end. But apart from that, the only thing you can have is pencil, calculator, and a ruler. It's probably not a terrible idea, especially if you have a habit of very squiggly lines when it comes to diagrams. Right? So all the data that you're going to need is going to be provided to you either in the form of a diagram or in the form of steam tables or some other piece of information. So you will need no external information than what is on the equation sheet, what is in the question, and what is provided for you on the exam. So no cell phone calculators, no computers, no tablets, just pencil, calculator, and a straight edge if you'd like to have one of those. Okay, any questions on the format or the content of the exam? It's going to go obviously from the beginning of class up through what was covered in homework 3. So that includes potentially a little bit of multi-component systems, but obviously the vast majority of what we worked on was not multi-component systems. There was a little, on the practice exam, there was a question on that as well. Okay, any questions? So we can run this 2 different ways. We can keep going until we run out of questions. I have some prepared content. It's not example problems per se. It's more of just a recap of how we got to where we are here. So it may be useful to some, maybe simplistic or repetitive to others. So if anyone has any specific questions, stop me at any point along the way and we can address any questions that we have. I forgot to print out the practice exam solutions to have ready, but if anyone has any questions on the practice exam, we can also cover that as well. You just might have to remind me of what the question is.
I've got a question on the first one on the practice exam.
Okay.
On the second, on part B.
Okay. What was the question? What was the question?
So this one's, so nitrogen is compressed reversibly and adiabatically.
Okay.
1 bar and 25 degrees C to 15 bar.
Okay.
So you calculate the final temperature in part A.
Okay.
And then in part B, you calculate the work.
Yes.
And in the solution in part B, you say delta U equals Q plus W, and Q is 0, of course.
Yep.
My question is more, don't you also have, I guess what I did is I said that you had the enthalpy, so du is equal to the enthalpy plus the work, and that's equal to 0. Is that, I mean, why is that not correct? Because that's going to give you a different value than what you calculated.
So for this one, let's focus on the energy balance here. So we have ds dt. This is a closed system, right? Or I guess it's not specified necessarily, right?
I guess no, it doesn't.
So we can do this. We can either do this as a closed or an open system. It'll get you the same result, just with some slightly different arithmetic. So if we say that this is an open system, we can imagine our system being a volume element of fluid traveling through a compressor, steady state. Then when that one goes through, another volume element comes and travels through. In that case there, we would say that ds dt is equal to 0, which is equal to the flow rate in terms of n times by the entropy in minus the entropy out plus q dot over t plus s dot gen. So this would be 0 because it would be adiabatic. This would be 0 because it would be reversible. In this case here, we have delta S is equal to 0. Right? Now let's do it as a closed system. In this case, ds dt is not equal to 0 because now we're envisioning this being a piston cylinder device that's being compressed. So this covers on some of the topics we're going to go over anyway. In this case, we don't have any flow rates in and out of the system. So this is just our heat over temperature and the entropy generation. Again, 0. 0, but now we're integrating from state 1 to state 2. Therefore, we get delta S is equal to 0 again. So it doesn't matter how we think about this problem. It's going to be exactly the same as an open system or a closed system. For the energy balance, we can say that du dt is equal to summation n dot h of I plus q plus w. So is the question whether or not we should be using u or should be using h?
Yeah.
You guys can see the wording of the question one more time, just to be clear on it?
Or why, I guess the question is why should H not be there? I guess you don't have a flow.
So we're trying to solve for the work.
Right.
So if we treat this as a closed system, then it's adiabatic. So it's adiabatic. So in this case, this is closed, this is 0, this is 0 here. So in order to solve for the work, this has to be equal to the delta U then.
Yeah, okay, that's true.
Now, envisioning this as an open system, the work required to adiabatically and reversibly compress. If it's adiabatic, yeah, I just have to think about this for a second. So I think I envisioned this as a closed system. Let me say it one more time here.
Certainly makes it easier.
In my solutions, I use delta H, delta U.
So you do delta U, you say Q equal plus W, and Q is 0, of course, and then you integrate, well, CV delta T. That's the solution.
Let me address this. Let me go over the details again. This is, to me, this makes the most intuitive sense. But let me double check my solutions again after class, and then I can get back to you on more details.
That matches with the.
Well, this matches with the solution, but right now I'm just sort of, I'm trying to, so this one makes sense to envision as both an open or a closed system. And this one here, I'm just trying to run through my head. Because if this were a open system, then du dt of the process would be equal to 0, and you could rationalize it would be delta H then in this circumstance here. But right now I'm drawing a blank on the exact distinction about why we would visualize this differently. But let me take a second and think about this, and I can look at this, what I wrote down in my old solutions. I didn't spend enough time looking over those. But this is what to me, this is what I would default to, because you're pressurizing it.
Yeah, I think as I look at it now, this makes more sense, to say it's closed and pressure.
Yeah.
I assume that. I got it.
I assumed it was a closed system too. It was an open system. Yeah, sorry, let me take a few more minutes to think about that one. Which is the point of the regrades there for that, in case I make a mistake in the problem itself. But anyway, well, this highlights a couple of the things that I wanted to talk about. First of all, the first part of the exam review was going over the first and second laws, which we have done so here. There's our first law that we conventionally use. Here is our second law that we conventionally use. A couple of terms that are important. Closed, no flow in or out. Adiabatic, Q is 0. Reversible, the entropy generation is 0. So if you have adiabatic plus reversible, then you know it's isentropic. That was kind of the first little talking point there. No, the only other thing too is that work. Another definition, if it's rigid, that means that that the volume is constant. Therefore, our work, which is minus dV dt, is going to be equal to 0. So that means there's going to be no PV work. I'm trying to think, is there any other tricks? No, that's about it. This is reversible and adiabatic. So for work, we have shaft work, which is an impeller potentially, or it can also be volume expansion work. Right? So we have shaft work, and we also have minus P dV dt. Those are two different forms of work. Shaft work, volume expansion work. Two different ways you can think about the system. Okay. So this is balances. So this is going to be one half of, I guess, a lot of the stuff we're talking about. Yeah.
Is there a way to pressurize an open system?
Is there a way to pressurize an open system?
I mean, a compressor is open, isn't it? I mean, you can think of it going through and then.
The system in a compressor, so if we have an open system compressor, then we would define our system as the unit of the compressor itself when we have flow pushing it in and flow pushing it out. So that's why I'm tending to default that this is the right energy balance we have right here, but but instead, if we follow an element of fluid as it goes through the compressor, can we really differentiate that as an open system or a closed system? So this here, I believe you could consider that exactly to be a closed piston cylinder device is what that would be. And you just reversibly and adiabatically compress it. Because in this case here, there's no flow going in or out. So then the key distinction is, in this case it's delta H, in this case it's delta U. How do we translate between the two of those? Because the difference, obviously, is just going to be the PV. So in this case here, we have a PV force pushing it in. In this case here, we have a PV force pushing it out, which is additional work that is not being done on the fluid. It's work that's being done on the system. So in a flowing system, it would take a little bit extra because you'd have that PV work going on it versus in the closed system, since it's adiabatic, the work is only related to the change in internal energy. That's the best answer I've got so far, is that if we were doing this here with work going into the system, I don't know if this is addressing what your question was, I guess. If we're doing our balance on the system, that means the act of the fluid flowing into the system is physically pushing and squeezing the fluid into the process. And then the process itself is physically pushing and squeezing the work out. So you get that little additional contribution here from the PV term, which would be distinct because that's not the work that it takes necessarily to pressurize that one element of fluid going through the system. Because the fluid itself doesn't necessarily have to be the one that's causing the flow. I'm not 100% satisfied with that answer, but it makes sense to me. Okay. Any more questions on balances? So again, strategies for taking the exam. When you see a question, break it down into its individual parts. Is it a balance? Is it a state change? Is it a phase change? What's going on in the system? Balance is one part of it. So the first half, and what we started with, is that we need an energy balance and an entropy balance as a way that we can interact with the system. The only way that we can interact with the system thermodynamically is by adding or subtracting work or heat to the system. We cannot ever measure internal energy or entropy. So the only way that we have a gateway into the thermodynamic world is through balances. So if we had perfect thermodynamic data already tabulated, which we couldn't have unless we did the other stuff, we don't need to do anything beyond a balance here, because we can just look up all the properties of interest that we necessarily want to look at, right? But if we don't have the data tabulated, that's when we need to look at state changes. And here the goal is to use the fundamentals of thermodynamics to give us a way that we can actually calculate how would the internal energy or the enthalpy or the entropy change as a function of pressure, temperature, or other conditions. So what we started off with is we took the first and second law and smashed them together. So the first law just says that the change in the internal energy is just related to how much heat or work that we put in or out of the system. We can rewrite the work as volume expansion work. In this case, we're not going to have any impellers or something like that, because ultimately, those impellers are just going to be a source of heat if it's frictional heating or whatever the case is, right? Like a pump impeller spinning, it just heats the fluid up by friction. The second law rearrange and solve for heat, combine the two together, and we have the combined first and second law. And this is our gateway into calculating state changes. This is how it all came together. But really, any expressions that you see on the equation sheet, all of these expressions in this whole category here of state functions and changes, every single one of these is just a restatement of the first and second law of thermodynamics. That's it. So they are 100% valid under all circumstances, because the first and second law have never been violated in the history of all of science and thermodynamics. Right? So all of those expressions are equivalent to this one right here. We're relating changes in internal energy to changes in entropy and changes in volume. And remember, those are the three fundamental variables that we decided that the universe is described as in terms of continuum thermodynamics. So that's sort of an integral part of thermo, is the, knowing that we need two variables to define a single phase. Now, if we add in some calculus, we can also relate changes in the internal energy to just changes in any function that we choose. So if we're clever, we're going to expand the changes in internal energy with respect to keeping track of only two additional variables, S and V. And from here, we were able to derive lots of expressions And if we put these two together, we can derive some thermodynamic identities. Such that temperature and pressure are derived quantities. It wasn't until Boltzmann and the kinetic theory of gases in the late 1800s where we had a physical meaning for the temperature. We always knew that hot was hot, but really couldn't describe why hot was hot. Right? We didn't have a good intuitive understanding of why temperature was temperature. So for most of the development of thermodynamics, temperature and pressure were things that we knew we could measure, but we really didn't understand why and what they were, so we only related them back through these continuum expressions. So effectively, they're defined quantities from a thermodynamic approach. They're not just these innate variables of the universe. They're useful properties to measure, but that's about it. Now, in addition to defining temperature and pressure, we also defined enthalpy. We define the Helmholtz energy and the Gibbs energy. And by extension, the fugacity. All of these expressions are just restatements of the first and second law of thermodynamics but rearranged and combined into new thermodynamic variables that are helpful to perform calculations. Enthalpy is helpful if it's not too confusing for an open system, because you have this additional PV term that's going on. So when you're looking at a constant pressure system, meaning that you might have some volume expansion work, then you can lump that in with your du, and you'll end up getting enthalpy term. So if you have a closed system at a constant pressure, then you can have an enthalpy system. Then you can have enthalpy. Okay. So the next step how do we actually measure the internal energy, the entropy, and all the other properties in the system? So what we did is to convert changes in internal energy to functions of changes in temperature and specific volume, and changes in enthalpy with respect to changes in temperature and pressure, entropy with respect to changes in temperature, pressure, specific volume. We have multiple expressions for the entropy changes. Entropy is actually a little bit easier to work with, which is always ironic, I think, because it's by far the most confusing of concepts, but the math always ends up working a little bit nicer when you work in terms of entropy. So to get to this point, this is where we threw in all of our little tricks, like the triple product rule, the chain rule, let's see, expanding, so this is the total differential. So this is the total differential here. We don't just take a derivative with respect to one variable, we take the derivative with respect to all variables. The only reason why we can do this in any practical sense is because we only need to define two variables for a single component, single phase system. So we took all these little tricks, we threw them at this problem here, and we ended up coming up with expressions for how the internal energy changes how the enthalpy changes, how the entropy changes, let's see, where's the entropy equation? No, I don't have it written down here on my notes.
CV over T dt.
Yeah, so we're on the equation sheet here. CV over T dt plus dp. And it also equals C sub P over T. I got that right. What we are looking at here is the combined first and second laws of thermodynamics. That is it. These statements are exactly equivalent to these two right here. Right? The only assumption that we've made in all of these calculations is reversible, is that the processes are done reversibly. So we've left out S-gen. That's it. Now the reason for that is if we just want to calculate a state change, we're going to want to walk through the process and do it in a reversible sense to make our lives a lot easier. So the only assumption that has been made in all of these calculations is that we are doing a process reversibly. So each one of these is equivalent, and as long as these are satisfied, the first and second laws of thermodynamics are happy. The only thing that we've done is we've defined some new variables like temperature and pressure. We've defined some new variables in terms of the enthalpy. We don't really talk about these too much because fugacity is much more useful, but really we could just calculate Helmholtz and Gibbs free energy if we wanted to using equivalent expressions here. But for the most part, the fugacity is a much more useful concept. Now, like I said, no assumptions are made at this point.
Except that the entropy generation is 0.
Exactly. So if I want to then use these expressions to solve, if I want to go from state 1 to state 2, that means the change in internal energy going from 1 to 2 is equivalent to integrating from 1 to 2 of any one of these individual expressions. This is going to be equal to the internal energy of state 2 minus the internal energy of state 1. So this poses a problem. The first and second laws of thermodynamics only tell us how the energy and entropy change as a function of external stimulus, right? Work or heat. But it doesn't tell us the absolute amount of energy in the system or the absolute amount of entropy in the system. Classical thermo does not tell us that information. So what we have to do is we have to define a reference state. And we can define that arbitrarily because negative numbers are just as valid as positive numbers. So if you choose a reference state that's at a high temperature and pressure, well then your steam tables are all going to be negative numbers. So hopefully everyone saw that when you're working through your math this week on question 3, I chose a starting point as an ideal gas as my reference state. So when I built my table, everything was negative. Then when I shifted it, everything became positive and reasonable. But if I were to use that table to solve a problem, it wouldn't have mattered what my reference state was. So in this case, we'll typically define a reference state that's convenient and just call it 0. I mean, we could call it 100, we could call it 1,000,000 if we wanted it to. Right? The reference states, it doesn't really matter. Because the reference state will always cancel out. Right? So if I have a table of temperature versus internal energy, for example, out of a bunch of values, so this will be 0, let's say this is 10, let's say this is 100, this is 1,000. All of these are calculated relative to the reference state. So if I wanted to look at the difference between state 1 and state 2, and this is the reference state, right? I'm really looking at U of this one is from reference to 100, U of this one is reference from 1,000. The reference state just ends up canceling out. Right, so if this was a 1,000,000, this would be 1,010,000, 1,100,000, 1,000,000, it doesn't matter. Okay, so that's the purpose of the reference state. So now the next step is I need to figure out how do I get from my reference state to whatever temperature and pressure conditions or specific volume conditions that I care about. No assumptions have gone into here. Now we have a row on the equation sheet that says ideal gas relationships. The ideal gas relationships are such PV equals RT. The ideal gas relationships are such that I have substituted the ideal gas law into each of these expressions and evaluated the integrals. That's where those equations come from. So if we take a look at the, let's say this one here. C sub P over T dt. If we assume that heat capacity is constant, so we're going to integrate this going from 1 to 2. We're going to integrate this going from 1 to 2. We're going to choose a path. We'll first go over a temperature path. We're then going to choose a second path where we go over a pressure path. So if I integrate 1 over T, assuming the heat capacity is constant, that gives me C sub P ln T2 over T1. Now this is, of course, assuming a constant heat capacity. If we don't have a constant heat capacity, then we have to use some sort of a polynomial or data expression for whatever the heat capacity is at all the discrete steps that we take. We don't have to have a function to evaluate these things. We'd like to. And that's why polynomial functions are typically used in the back of thermodynamic books, because polynomials are very easy to integrate. but we could evaluate this numerically. So if I had tabulated data of the heat capacity as a function of temperature, I would just have to choose a discrete step size and numerically evaluate this integral. We're all crystal clear on that? This next one here, for the ideal gas law, we have to evaluate the expression. So this is delta S going from T1 to T2. Now, next step is delta S going from P1 to P2. This is the integral from P1 to pressure 1 to pressure 2 of minus this specific integral. Right, what is the partial derivative of the specific volume with respect to temperature for the ideal gas law? R over P. So again, it looks very, very similar. So this is ultimately going to be equal to minus R ln of pressure 2, pressure 1. And that should be exactly the expression that we have the first entry in our table. If we have an equation of state that is not the ideal gas law, then we have to substitute that equation of state into these expressions and evaluate, which everyone should hopefully be very intimately aware of based on the homework that we did that was submitted today. So this concludes all single phase work that we did. So to solve any problem of any real fluid, we have to start off with an entropy balance and an energy balance. And then from these two balances, we're going to have some unknown quantities, whether it's the entropy in or the entropy out, or it's the internal energy change, whatever the case is. Then we're going to use these expressions of the first and second laws of thermodynamics with an equation of state to allow us to calculate properties of the system. Yes?
When we are doing calculation of state changes from going from one state to another, do we have to assume that there is no phase change, or we don't care if there is a phase change?
These are only good for single phase systems, these expressions here. So all of these are only good for single phase expressions because when we talk about a phase transition, we're talking about first order phase transitions. So a first order phase transition is where we have a discontinuity in one of the properties. So I believe, let me get this one right here, the dg dt, I think this is on my equation sheet here. Is it on here? Let's see. It is, good. dg dt, so the change in Gibbs as a function of temperature at constant pressure is equal to the negative entropy, and the change in Gibbs free energy as a function of pressure at constant temperature is equal to the specific volume. And likewise, we also have the change in Helmholtz as a function of volume at constant temperature is equal to the pressure. We could go on from there. dA dt at constant V is also equal to entropy. But anyway, actually this is not good. Let me erase this one. Forget about that. So, at a phase transition, there is a discontinuity in the properties of the system. So there's a discontinuity in the enthalpy, there's a discontinuity in the entropy, there's a discontinuity in the Helmholtz, a discontinuity in all these properties. So that means we cannot integrate this function as if it were smooth and continuous. So these values are only good when you don't have a first order phase transition, because there is a step change, meaning that if I look at the entropy as a function of my reaction coordinate, let's say the path that I'm taking, I'm going to be down here low, I'm going to have an instantaneous jump and be high. This is my liquid, this is my vapor. The slope here is a discontinuity, so I cannot evaluate that expression at a phase transition. But good question. And that transitions us on to phase transitions. So for one component multi-phase systems, we established a series of equilibrium criteria. We had thermal equilibrium, where all of the temperatures had to be equal. We had mechanical equilibrium, where the pressures had to all be equal. And we had chemical equilibrium, where the Gibbs free energies all had to be equal. Now, how we got to this point is we effectively took a similar expression like this, but for an open system. And in order to satisfy that the change in entropy for each of the two phases was 0, the only way it could work out is if these three expressions were true. But ultimately, what we care about is that the Gibbs free energies are constant across all of the individual phases. We also talked a little bit about the stability criteria. So the conjunction of these two at equilibrium basically means that entropy is maximized at equilibrium. Right? You could envision a scenario here where equilibrium was satisfied if you had a minima in the entropy. But ultimately that would result in a system that is an unstable fluid. And so you have to have entropy as always a concave function. It always has to be frowning down as a function of any change. Time, temperature, pressure, internal energy, volume, anything. Entropy always has to be a concave function, otherwise the universe is fundamentally unstable. Now the reason why we care about this is because it lets us know that heat capacity always has to be positive. That kind of makes intuitive sense. But specifically, that pressure and volume always have to have an inverse relationship. And this is the tool that we use to allow us to calculate phase transitions using a cubic equation of state. So if we look at isotherms, PV isotherms, so plotting pressure versus specific volume, isotherms are where we plot out how the pressure and volume relationship changes as a function of temperature. So way up here, oh, sorry, no, that's not right. Let me just do this. That's super critical, it's not what I was trying to show you. So over here, the system should behave like an ideal gas. Very high specific volume or low density and very low pressure. But as the fluid gets closer and closer and closer to a phase transition, the cubic equation of state kind of gives us a shape that looks a bit like this, where we have a stable fluid at very low specific volumes or high densities. This is going to be our liquid phase. We can remember because liquids are dense, so that means they have a small molar volume. Gases are not dense, they have a high specific volume. Also, if your specific volume is all the way down here, that means you're at a high pressure. If you're at a high pressure, you're more likely to be a liquid. If you're at a low pressure over there, you're more likely to be a gas. So we talked about at phase equilibrium, we can imagine some special pressure that we now know as the vapor pressure at that temperature isotherm, such that it satisfies that when we integrate along a path of this isotherm, that the delta G of the phase transition is 0, which is the case that we can grab from this intuitive sense, right? If phase 2 is the vapor and phase 1 is the liquid, transitioning from phase 1 to phase 2 is delta G, which is 2 minus 1, which is 0. It's the same. The Gibbs are constant. So that let us know that if we cancel out these areas here, because in this case, that's the expression we use to integrate to get delta G, so I'll recap. then we can use this information for phase transition. Now, eventually, let's see, I define fugacity on the next page. If we look at the shape of the curve as we increase the temperature, we're going to have a two-phase region, but it's going to get smaller and smaller. That's because we're approaching the critical point. Smaller and smaller, and eventually we're going to hit an inflection point that's also a zero slope, and that is going to be our critical point. So this is going to be TC, PC. And then above, we're not going to have an inflection point. Let's see, no, we will have an inflection point. No, we won't. So if it ever does negative, it'll start to smooth out, so it'll never get to a zero slope. It'll always stay. You could have inflection points, but you can't ever have the slope be negative. So when we draw the two-phase region, we are connecting all of these different points. So when we look at a phase diagram that's already been constructed using a cubic equation of state, we have no squiggly lines. Because the real fluid process, what it does is it goes until it hits the two-phase boundary, then it condenses, and then continues back up again. So if you're using an equation of state to calculate state changes, like in these examples here, we need to make sure that we're very far away from a condensation process. Because you could inadvertently go from, let's say, here to here unwittingly, in which case you'd have some sort of crazy weird result. So if you're doing state changes with a cubic equation of state, you need to make sure that you're far away from a phase transition. Otherwise, you can get yourself in trouble. One trivial way to do it is just make sure you're supercritical. If you're supercritical, then whatever. You're never going to have a phase transition anyway. So we can solve for vapor-liquid equilibrium using this area canceling out approach by making sure that delta G is equal to 0, but it's kind of a little bit clunky. It's not critical that we define fugacity, but it's convenient to define fugacity now. This is effectively a Gibbs departure function. That is scaled. So we define fugacity. We have the fugacity coefficient, which is the fugacity divided by the system pressure. This is the Gibbs free energy as a function of temperature and pressure, normalized by the Gibbs free energy of an ideal gas at the same temperature and pressure, normalized by this RT factor, and then we kind of take the exponent and lump it in to make it a little bit more convenient. But this is our definition of the fugacity. If you rearrange it, you can get many, many equivalent different forms. So if we use this, that means at equilibrium, the fugacity of the liquid is equal to the fugacity of the vapor, which is equal to the fugacity of any number of phases that we have in the system. Now, we hinted at this a little bit on Monday. The reason why we have to define the fugacity, we don't have to, I guess. The reason why it's really convenient to define the fugacity is not because of single component multi-phase systems. It's because of multi-component multi-phase systems. Because the partial molar Gibbs, which is equal to the partial molar enthalpy and entropy. This is equivalent for a multi-component multi-phase system, and the issue is that the partial molar entropy has a discontinuity in it. So that's why we define the fugacity as the deviation from the ideal gas behavior, because the entropy's partial molar property for an ideal gas has that discontinuity built into it, meaning that we can subtract away the discontinuity if we define the fugacity. Not critical for the exam, but something useful to highlight. All right, so we did a similar approach with all of this junk over here, and we could come up with expressions for how to calculate the fugacity. Right, this is how we can calculate the fugacity with an equation of state. Now, this expression is not particularly useful because that requires us to have a volume explicit form of the equation of state. This RT over P, this is the volume of an ideal gas. This is the volume of a real fluid. And that's how we get the deviations here, because this is how we started off. Right, we're calculating the change in Gibbs free energy going from an ideal gas state to some finite pressure. So if we did that same path for this simple expression right here, right, so the fugacity is not complicated. We just take this expression of the Gibbs free energy as a function of pressure. We subtract what the Gibbs free energy would be for an ideal gas. All we're doing here is we're substituting R times T over pressure for the ideal gas, and then we integrate it. Right, so that's it. Right, so fugacity is not terribly complex. But all of our good equations of state are pressure explicit. So they're all functions of specific volume. So with a little bit of arithmetic that was done on the homework, we can rewrite this expression so that it is a volume explicit expansion. Again, you don't need to remember these equations. If you look on your equation sheet, we have fugacity, equilibrium, and mixture relations. The first line defines all of these fugacity functions. We don't have to remember these. We just have to remember how we got here. Okay, we talked a little bit about liquids and solids for fugacity. For the most part, we talked about pointing corrections. So the fugacity of a liquid is going to be equal to the fugacity of the saturated system with an additional term. We could also include an additional pointing correction for a small system. And this was, to the internal pressure. Right, so these are pointing corrections. One of them is for systems that are far away from the saturation point, and this other one here is for systems that are very small, sub-micron size, because their fugacity is going to be modified as a result of having high surface interactions. Now, the multi-component stuff we talked about on Monday, so I won't cover it too much, but I wanted to highlight one aspect of the multi-component systems while we still have a chance. So go over the definitions for multi-component systems. Right, we define concepts as the partial molar. Right, we had the pure species property. We had the property of the mixture. We had property changes of mixing, right, which we could write as just one definition away. Theta over bar is defined as these are a bunch of the definitions that we have for the multi-component systems. Just be familiar with what those terms are. Now, one area that we didn't talk a lot about is if we have a mixer. Call this stream 1, it's going to be component A. Call this stream 2, it's going to be component B. I'm going to call this stream 3, and it's going to be a mixture of A and B. So for any real system, if I mix A and B at the same temperature, the outlet is almost never going to be exactly the same temperature. It may not be close enough that we don't care too much about it. We can approximate it as being the same temperature. But what we're looking at here, this is the classic adiabatic mixture that we talked about earlier on in the class. We had homework problems on this. If we do the energy balance on this system as an adiabatic mixer, du dt is equal to 0. We're going to model this as an open steady state process. It's going to be equal to the flow rate of A times by the enthalpy of stream 2 plus the flow rate of, B. I screwed this, let me do A and 1, that makes more sense. Plus B and the enthalpy of stream 2 minus the combined flow rate times by the enthalpy of stream 3, which will be, that's it, right? Because it's an adiabatic mixture, no work, no heat going on in the process. Now, the question here, this aspect, we've already done lots of, right? This is just state changes of a single component system, so it's pure fluid. Now, when we did the adiabatic mixer previously, what we effectively did was modeled A and B as two independent streams that weren't mixed. We cannot do that anymore for a multi-component system. So instead, we have to look at how the mixing properties change. So what we care about then, if I look at a plot of the enthalpy of a mixture as a function of the mole fraction of, let's say, component A in the system, this dashed line is going to be the ideal mixing, and that's what we previously had done. The real system is going to be some difference. Either it could be positive or it could be negative. And the shape can be wild all over the place. In this case here, the enthalpy change of mixing is greater than 0, so this is an endothermic process. In this case here, the enthalpy change of mixing is less than 0. This is an exothermic process. What I need is in order to perform this calculation, I need to know what is the enthalpy of my outlet stream. So that means I need to take all of these different concepts and terms here and rearrange them to solve for this property based on the pure system properties here and the change in mixing, which is typically measured with a calorimeter. Now this is a relatively straightforward problem, right? This is the enthalpy of the ideal mixture. This is the enthalpy of the real mixture. The difference between the two just has to be accounted for. Does that make sense? It's just an arithmetic rearranging between all these different expressions. Now, the problem gets a little bit more complicated. If, let's say, A and B are at different temperatures than the outlet is at, right? The key thing is the outlet, we need to know what the heat of mixing is as that function of temperature and pressure, because it's all going to change. But we can control how we do the mixing process. Right, so let's say A enters at 100 degrees C, B enters at 25 degrees C, and this is leaving at, let's say we have a chart here. Actually, this is going to be confusing. We have to make sure that this is leaving at, say, 50 degrees C. We could use this information to basically figure out what the heat of mixing is, for example. But what we would have to be clever, we would have to first cool this down to 50, heat this up to 50, and then mix them at the constant temperature. Right, so we can control how the process goes on. We don't necessarily have to Just imagine that we're actually pouring this into a bucket and hope it all figures out and works out correctly. Right, but this is something we didn't really talk about when we were talking about multi-component systems. But the energy balance hasn't changed. The only complexity in this relationship now is how do we estimate the enthalpy of the outlet stream? And from there, we have to have some sort of experimental information about how the mixing properties change. All right. Any last minute questions? So I'll hold a brief help session tomorrow for any last minute questions. What time works best for people? Should we do noon to 1, which is kind of the office hours time? Is that okay, or do you want to do the same as the class time? Which do we prefer?
I like noon to 1.
That's really good.
Noon to 1 it is then. All right. Good luck. See you on Friday.